Chemistry. How are we doing today? Hopefully everybody is doing well. Today we are going to be continuing our notes on part 2 of intermolecular forces. So before that, you do need to make sure that you've got your notes, you've got something to write with, and then it a lot of times never hurts to have your periodic table to help you along with these notes. Okay, so we're going to start with surface tension for a factor that is going to be affected by our intermolecular forces. Now, a factor is basically just a thing that is going to be affected by those IMFs, all right? So for surface tension is basically the resistance of a liquid to an increase in its surface area. Okay, so what do I mean by that? Well, what I mean is that if I take something like water and I want to increase its surface area, I'm going to have to actually push it out, right? I'm going to have to spread it out across the table. Well, if you notice, water will bead up when that happens. Why does it bead up? Because it's got that natural attraction to itself. And so because of that, it's going to resist that actual change in the surface area. And so this is actually the reason that when you, for instance, jump in the pool and you do a belly flop, right? When you do a belly flop in the pool, you slap that water and it hurts. Now, why does it hurt? Well, it hurts because that water is resisting that change in surface tension, right? Or sorry, that change in surface area. And so surface tension is that ability for the substance to resist the change in its surface area. Now, this tends to follow the trend of, or it does follow the trend of, the stronger your IMF, the higher your surface tension. Now, why would that make sense? Well, it makes sense because if I've got a stronger connection, a stronger force between those two molecules, what I'm going to see is that that surface tension is going to be higher because it's going to take more to actually break that bond, break that force that's holding those two molecules together. And so with a higher surface tension, with a higher IMF, we're going to see a higher surface tension because it is harder to break the bond because it's got a stronger IMF. Okay? All right, so that was surface tension. So now let's talk about capillary action. So capillary action is basically the spontaneous rising of a polar liquid in a narrow tube. And there's two reasons this can happen. There's two forces that we can see occur. This is a cohesive force and an adhesive force. So what's the difference between them? Well, a cohesive force is going to be the intermolecular forces among the actual liquids, okay? So it's going to be the forces that actually hold that liquid together. Now, what we do end up seeing is that the IMFs in these liquids are going to be pulling on each other. And again, that's why surface tension, for instance, actually changes, right? With your surface tension, the top molecules are actually attracted to the molecules below them. And so we actually see that pulling down, and so it does resist that change because they're all trying to hold together, right? An adhesive force is basically going to be a force between the liquid and its container, okay? Now you're like, okay, the liquid and its container, but a lot of times our containers are things like glass. Well, glass is actually a polar material. And so because of that, if you've got a polar substance, it's going to be attracted to the walls of that. And so when we do things like put water into a graduated cylinder, you do see that meniscus that forms. Why? Because the water is attracted to the glass on the outside of that. And so because of that, the water actually pulls up and away from the rest of the water molecules. Convex tends to happen. So convex would be a dome in the other direction. So instead of forming a meniscus that's down and up, it's going to form a meniscus that goes up and then comes back down, right? So mercury will actually do this. Now, mercury is going to be an example of a non-polar substance, and it can produce a convex meniscus. Why? Because those molecules are attracted more to themselves than they are to the container, right? The polar container is going to attract polar things. The non-polar container would attract non-polar things. And so depending on the container that you're using, you can actually get these concave and convex menisci. And so that's what we're seeing right here. All right. So that would be your capillary action. And so capillary action is, again, going to be those two forces that are causing it to pull in one direction or another, either towards the molecules themselves in the liquid or towards the container that they're in. Okay. Now, the next one we have is viscosity. Now, a lot of times when I think of viscosity, I think of some kind of oil. So I'm going to be thinking of like vegetable oil or, canola oil, or if we're looking at something like motor vehicles, we could talk about crude oil, or we could talk about the synthetic oils that we put into our vehicles. Those are all going to be talking about highly things with a very viscous consistency. And viscosity basically just means it's resistance to flow. So it's basically the resistance of a liquid to actually be poured out of its container. Now, if I take something like water, well, water is not very viscous, right? Water, if I turn it, basically immediately turns to the exact thing that it was. Okay, so if I take something like water and I turn it on its side, what do you notice about the water? Well, the water is actually going to be quickly moving to change that, right? It's not resisting that flow really at all, okay? Now, if I take something like dish soap, turn it on its side, what do we notice? Did it resist that flow? Yes, it did. Now, liquids with a large IMF, a large intermolecular force, do tend to be highly viscous. And an example of that would be something like glycerin or glycerol. And so what is glycerin or glycerol? It's a lot of times what's in something like soap. It's kind of what helps keep those suds together when you're soaping like dishes or something like that. Now, one of the units that we do use for viscosity is a poise. And so the poise is basically just 1 gram per centimeter over a certain period of time. So in this case, it's going to be a mass per centimeter seconds. So it's basically if I take 1 gram of that substance, it can move this many centimeters in this many seconds. Okay. And so that's what a poise is, 1 gram per centimeter seconds. Now, often it's going to be given in centipoises. And so, for instance, water has 1 centipoise at room temperature. Okay. And here's some examples of viscosities of several hydrocarbons, right? Now, these are pentane, hexane, heptane, octane, and nonane. Now, these all in general have the same structure. They have the same intermolecular forces. And so what we see is as we move down, again, you're noticing that their formula is essentially the same, right? All we're doing is adding that CH2 to the middle of it there. But if you notice, your viscosity here is also going to be increasing as we move down. Why do you think that is? Well, because each of these have the same structure. The only thing that's changing really is their mass, right? And so with our mass changing, as we're increasing that mass, we learned that if we've got the same intermolecular force, we do actually have to take into account our molecular weight. The thing with the greater weight is going to have a greater intermolecular force. And so that's what we are seeing right here with our viscosity increasing with those intermolecular forces. Okay? All right. So next thing we have is vapor pressure. So vapor pressure is actually an extremely important thing that you know for the AP exam. It is tested pretty much every single year. So I want to make sure that I really want to make sure that y'all know what to do for vapor pressure. So for vapor pressure and changes in state, first off, we need to know what vaporization or evaporation is. So vaporization is an endothermic process. Why is it endothermic? Well, it's endothermic because we have to add energy to actually break those intermolecular forces, to break that intermolecular bonding that occurs. So again, if we're going to be increasing that temperature, it's because we're actually going to be absorbing that energy into that substance, which is breaking those IMFs. Okay. Now, with that, we do have something called heat of vaporization. And basically all that is the amount of energy that's required to vaporize 1 mole of a liquid at a pressure of 1 atmosphere. Okay? And so what we've learned is that if we have an increase in our IMFs, we will actually see an increase in the heat of vaporization. Why? Well, again, if you've got a high IMF, those molecules are very attracted to one another. And so as a result, to actually remove them from each other, we're going to have to apply more energy, right? And so because of that, since heat of vaporization is the energy required to vaporize 1 mole, that energy required is going to increase, all right? It's kind of like I like to think about IMFs kind of like magnets. The stronger the magnet, the more energy it's going to take to cause those bonds or that attraction to the magnetic object to actually break, okay? Now, evaporation is a cooling process, okay? So evaporation is a cooling process. Now, what do I mean by that? If I talk about endothermic, how does that mean it's a cooling process? Well, so think about it kind of like this, right? When I go through evaporation, how does your body work? How does sweat work? Okay, if I get sweat on my skin, why does it feel cooler as it dries? Well, it feels cooler because as you evaporate, that heat is being absorbed away from you into that water, and that water is then floating away, right? And so what we see is that evaporation actually can cool something down some, okay? Now, next thing, condensation. Condensation is going to be the process where a vapor reforms into a liquid. So it's where we're taking something like that water vapor, steam, and we're actually condensing it, cooling it to where it will actually turn back into a liquid. Now, condensation. If evaporation, which was making it go from a liquid to a solid, is endothermic, then condensation would need to be exothermic, right? And so what we're going to see is that that energy is moving away from the water, and so the water itself would be cooling down, all right? Now, we do talk about dynamic equilibrium. And basically, for now, what you need to know is dynamic equilibrium is that the rate of condensation equals the rate of vaporization, okay? So the rate of condensation equals the rate of vaporization. So what do I mean by that? Well, what I mean is that if I've got dynamic equilibrium, that means as something is evaporating off, more is condensing on, okay? So basically, as one's going up, the other's coming down, and they're going to be in equilibrium, so they're doing it at the same rate, okay? All right, now, vapor pressure. Again, I told you that this was very, very important. So vapor pressure is the pressure of the vapor at equilibrium. All right, so we already talked about dynamic equilibrium and how it's the pressure going out is the same as the pressure coming in. So your vapor pressure is going to be when we reach that equilibrium. Now, the pressure of your vapor comes from our atmospheric pressure, so the pressure of all the air around us, minus whatever is in what we call a mercury column, so a barometer, right? And so basically it allows us to actually figure out what pressure is being exerted by the actual vapors on that. So what is vapor pressure, though? So we know that over time, liquids will evaporate, right? Because they're going to absorb energy from the air. And so once they reach that point where they have enough energy, you'll see those molecules start to actually go into the environment. Now, for that, how do we know what amount of pressure is actually being exerted by that liquid? Because again, as we're evaporating off that liquid, what we're going to see is there's going to be a buildup in pressure. Now that pressure is going to change based off of the container that it's in, right? But eventually we should reach a point where it's consistent no matter what size of container we put it in, okay? So what do I mean by that? Well, a barometer. How does a barometer work? Well, basically you've got a tube that's inverted. It's upside down, and it's got mercury that's filled up inside of it. Okay? Now, this mercury is floating around inside of this jar. And then on top of this, we're going to have whatever liquid we're looking at, right? Whatever vapor we're trying to observe. And then the atmospheric pressure is actually going to be pushing down on the mercury that's sitting here. Now, when the pressure gets higher, what we're going to see is that the levels inside of this are actually going to increase. So the levels in here will actually start to rise. Now, what does vapor pressure mean? Vapor pressure would be this substance right here actually slowly turning into a gas. Okay, and so we're slowly turning into a gas there, and then that gas is now going to be exerting downward pressure. It's going to be pushing away from the top of that container. Okay, and so because of that, we'll actually start to see that the levels will rise and fall until that vapor pressure equalizes out against the pressure in that atmosphere. And then the barometer, its job is to basically give us a line to say, hey, this is what it is then. Okay, and we'll talk about that in just a little bit more. But for vapor pressure, again, we're basically just trying to look at, I've got atmospheric pressure, and then I know how much pressure is now inside of my barometer. Okay, now, the weaker the attractive forces between the molecules, the more molecules there will be in the vapor. So what do I mean by that? Well, what I mean is that if I've got an IMF, and the IMF is very, very weak, that means there's no attraction or very little attraction to these molecules, right? And so because there's very little attraction, they're very easy to pull away and turn into a vapor. And since they're very easy to pull away and turn into a vapor, they're more likely to pull away and turn into a vapor. And so what you'll see is that if I've got a low IMF, my vapor pressure is actually going to increase. And if I've got a very high IMF, my vapor pressure is going to decrease. Okay, so the vapor pressure is going to be much, much higher if I've got a weak IMF because those molecules are not attracted to each other as much. Okay, so basically, again, the weaker the attractive force, the higher your vapor pressure is actually going to be. The higher the vapor pressure, the more volatile. And basically, volatile is just how likely it is to evaporate. Okay, now there are two factors that can affect your vapor pressure. The first one is going to be molar mass. Now, at a given temperature, heavy molecules have a lower velocity, right? We know that a big difference between for instance, let's talk about solids, liquids, and gases. If we've got a solid, its amount of energy is going to be much less than that of a gas. Like the movement that's going on is much less. Now, why is it less? Well, it's less because there's more molecules in a smaller area, right? So if we're talking about molar mass, heavy molecules are going to have lower velocities than light molecules. And thus they're going to have a lower tendency to escape their liquid surface. So basically, since I've got very heavy molecules, they're going to be less likely to actually detach and float away because they're going to be in a better place sitting down in the bottom of that. Okay, I like to think about it as it's harder to get up it's harder to pick up something that is heavier than it is something that is light, right? If I pick up a feather, that takes a lot less energy to pick it up and move it versus something like a 500-pound weight, right? I would not be able to pick up that 500-pound weight without either a lot of muscle or a lot of energy being exerted. Okay, so basically to sum that up, for your molar mass, if you've got a high molar mass, you've got a low vapor pressure. Again, because those molecules are not going to be easily turning into a vapor. Now, intermolecular forces, if we've got a strong intermolecular force, their vapor pressure is also going to be very low. Okay, so again, I like to think of these kind of like magnets. If I've got a magnet, is it very likely to detach from something if it's a weak magnet versus a strong magnet? The weak magnet is much, much easier to detach, and so it's going to have because of that, the vapor pressure is going to be much higher because those gases are going to be easily released into the container. Versus if you've got a strong intermolecular force or a strong magnet, what we're going to see is that those gases are not very likely to be released, okay? And so your vapor pressure would be lower. So right here, we're supposed to explain the differences between the vapor pressures here in the diagrams. So let's take a look at what's actually going on here. So this first one right here, this is going to basically be your control, right? So this is saying, okay, I've just got a vacuum. I've got nothing else in there. And so it's just the vacuum with liquid mercury, and then we've got atmospheric pressure. Now, the atmospheric pressure is pushing down, and right here would be the result, 760 torr, which is essentially 1 atmosphere. Okay. Now, I take some water, and I put it into this barometer. Okay, so I took some water, and I put it in this barometer. And what I found was that my pressure did change. Now, my pressure changed to 736 torr. And so what I would do is I would take the pressure of the atmosphere minus the pressure of the mercury there, or what's that mercury is measuring. And then I would get the answer, which would say, okay, well, my water has a vapor pressure of 24 torr. Okay. Then I look at this C2H5OH, which is ethanol, and I look at ethanol, and I'm like, okay, well, ethanol has, if you look, dropped down to 695. Okay, so again, I take my atmospheric pressure, and then I'm going to write these out, atmospheric pressure. And then I've got the mmHg, which is, again, basically torr, right? And then what I'm going to do is subtract those out, and I find that my ethanol has a vapor pressure of 65. Okay, well, if you notice, between water and ethanol, there is a change in our pressure, our vapor pressure. So we'll take a look at that in just a second. All right, then the last one I have is diethyl ether. Okay, y'all probably don't know what that is, but diethyl ether. And with my diethyl ether, what do you notice about our barometer here? Well, what you should notice is that there was a very large drop in that mmHg, right? And so because of that, again, we subtract them, and you'll find that we've got 545 torr. Okay, so why did this change? Well, let's think back to our rules. Well, first off, we know vapor pressure, there's two big factors, right? There's molar mass and there's intermolecular forces. Okay, so before we do anything, let's look at our first one, molar mass. Well, water has a molar mass of about 18, right? Ethanol has a molar mass of about 46.0, and then we've got dimethyl ether, and it has a molar mass of 74.14. Okay, well, if we followed our trend with vapor pressure, if I have a high mass, I have a low vapor pressure here, right? Well, that's not what we're seeing here, right? What we're seeing here is that with a higher mass, it's going to actually have a very high vapor pressure. But you're like, wait, but that doesn't make sense. Like, that's contradicting it, right? Well, again, if you remember back when we talked about IMFs, typically the only time we've taken into account our molecular weight is if the IMFs are the same. Okay? All right. So let's just remember that, right? So if we take into we only take our molecular weight into account if we're looking at the same IMF. Okay. So if I were to draw out each of these structures, what I would find is that water and ethanol are polar, and diethyl ether, sorry, I'm having trouble saying that apparently today. So our diethyl ether is going to actually be nonpolar. All right, now since that's a nonpolar, all right, let's take a look at this. The only type of IMF exhibited is going to be LDF. Okay, so we know that if I've got LDF, it tends to be the weakest IMF. And so if we've got a low IMF, we've got a high vapor pressure. And so that's actually what we see here with this diethyl ether. Okay, so diethyl ether, we've got a low IMF, so our vapor pressure is very high. So let's compare our ethanol and our water. So ethanol and water both actually exhibit hydrogen bonds. Okay, so we actually can see hydrogen bonds for both of these. Okay, but you're like, okay, well, but then if I'm looking at them and they're the same, then that would mean we compare our molar masses. Well, yes, but something else to keep in mind. Think about water and think about ethanol. Water forms two different hydrogen bonds. Okay, it's going to form two different hydrogen bonds. You've got your oxygen, you've got your two hydrogens here, you've got your lone pairs right there, and then this hydrogen is going to bond to. Please release group B. Release group B. Sorry. So this is going to bond to another oxygen there, and then we're just going to down here. We've got our hydrogen, and it's going to actually bond to. Get that erased. And it's going to bond to another water. And so for each water molecule, we're actually going to have two hydrogen bonds that form. Versus our ethanol, we're only going to see one hydrogen bond form. And so because of that, water actually has twice as many hydrogen bonds that have to break before it will actually be released as a vapor. And so since it's going to take two or twice as many bonds to break, the amount of energy is going to be higher, which means your vapor pressure is going to be lower. All right. And so when we're ranking these, the reason that our water has a lower vapor pressure, even though they're both sharing or they both have hydrogen bonds, is that water has actually two hydrogen bonds it forms versus the ethanol only is going to form one. Okay, so moving on. Now, one thing to keep in mind is that as our temperature is going to increase, our average kinetic energy increases, and more particles are going to have enough energy to vaporize. So what do I mean by that? Well, essentially, if I increase the amount of energy or the temperature that the substance is, now we've got more particles that are moving around, which means we've got more space between those particles, which means they are much more likely to actually vaporize, right? We're going to start overcoming those intermolecular forces. Now, the normal boiling point is the temperature at which its vapor pressure of the liquid equals 1 atmosphere. Okay, so that's going to be the normal boiling point. It's basically when we are exceeding our atmospheric pressure and becoming a gas, essentially. Now, the lower the external pressure, the lower the boiling point will be for the liquid. So what does that mean? Well, it means that if you go to a place with a different pressure, you're actually going to have a different boiling point. Okay, so water actually boils at a different temperature up in like the Himalayan mountains than it does at sea level. Okay. All right. Now, I've got this Clausius-Clapeyron equation. So what is it? Well, in the grand scheme of things, you don't have to do a lot of math with this. Essentially what it is it's showing that there is actually a linear relationship between vapor pressure and temperature. Okay? So there's a linear relationship between those two things. And so that's essentially all that equation is for now. If you take other chemistries in the future, you might have to go into it a little bit more. But really, it's just recognizing that there is that linear relationship. So let's take a look at the boiling points, the trends with boiling points using your IMFs. So based off of what you know about IMFs, what trends would you see with your boiling points? essentially what your trend would be is as your IMF increases, your boiling point will decrease. Increase. Wow. As your IMF increases, your boiling point will also increase, okay? And so, again, let's think about that. Well, what is boiling point? Well, boiling point, again, is us taking that liquid, overcoming the intermolecular forces of it so that it actually will turn into a gas. And so to do that, I do have to increase the temperature, right? And so the more my intermolecular forces are holding onto those molecules, the more energy it's going to take. So the higher the IMF, the higher the boiling point. And that's essentially what we're seeing over here. The stronger your IMF, the higher your boiling point is going to be. Okay. Now, rank these substances from lowest boiling point to highest boiling point. So I do want y'all to quickly pause your video and actually work through that real quick. Rank those from lowest to highest. Okay, so hopefully y'all got fluorine, sulfur dioxide, ammonia, water, germanium, and then salt. Okay, so how did we get that? Well, looking back, your fluorine has LDF. Sulfur dioxide is dipole-dipole. NH3 is hydrogen bonding. H2O is hydrogen bonding. Germanium is actually going to have properties of a metallic bond. And then NaCl is going to be ionic. All right. And so looking at this, we can actually see, we know that we're going from LDF to dipole-dipole, then to hydrogen, and then to other hydrogen, and then to metallic, and then to ionic. Now, those two hydrogens, you did need to take into account their molar masses. So the ammonia has a mass of 17.03, and then the water has a mass of 18.02. Okay, and how did I know about these? Well, if you remember back at the beginning of your notes, last class, Mrs. Treese actually talked about what we see right here. And so I've got LDF, which tends to be the weakest of the attractions, then dipole-dipole, hydrogen, metallic, ionic, and then covalent network solids. Okay, and we'll actually cover how to figure out if something's a covalent network solid in a few classes. Okay, so to wrap all this up, to essentially sum it all up, what are our factors in terms of IMF, and how do IMFs affect those factors? So if I've got a strong IMF, what it means is that I've got a high melting point, a high boiling point, but it means I've got a low vapor pressure. It also means I've got a high viscosity, surface tension, heat of vaporization, heat of fusion, and then last I'm going to have a lower volatility. Remember, if I've got a high vapor pressure, I'm probably going to have a high volatility as well. All right, y'all. So that is it for our IMFs. Please reach out if you've got any questions, and y'all have a great rest of the day. Bye, y'all.